Hello everyone, I'm Jiayu. I'm going to introduce our work, Non-parametric depth distribution modeling based depth inference for multi-view stereo. This is a joint work with Jose and Miaomiao. Multi-view stereo aims to reconstruct a 3D model of a scene from multi-view images. It is a fundamental problem for computer vision and has many applications such as 3D reconstruction and virtual reality. Recent MVS networks use a cost-to-find pipeline to efficiently leverage high-resolution images for multi-view depth inference. These methods estimate a coarse depth map in small resolution and gradually refine the estimation until reaching full resolution. While these approaches achieve promising results, they tend to miss small objects and boundary regions with abrupt depth changes. The main reason is that they make an early decision at coarse level under an unimodal depth assumption, and the error is propagated into refinement levels that cannot be corrected. To address this problem, we propose the NP-CVP MVSnet, a cost-to-find MVS network based on non-parametric depth distribution modeling and sparse cost aggregation. Our network can achieve superior performance on tiny objects and boundary regions. Our key insight is that pixels are the projection of a group of 3D points with different depth values. 3D structures across the boundary of an object are inherently multimodal distribution. For a pixel in coarse level, its corresponding pixels in the full resolution patch can be treated as depth observations, and its depth distribution can be approximated by the histogram of those observations. Arbitrarily assuming this multimodal distribution as a unimodal one will cause errors, especially on boundary regions. Given a multimodal depth distribution on the initial level, existing methods assume that the depth follows a unimodal distribution and use the expectation as the estimated depth. The estimated depth will be somewhere between the modes and is far away from the ground truth depth. The error will be propagated to the refinement levels and cannot be corrected by local depth search, resulting in incorrect depth estimation. To address this problem, we do not make any assumption of the depth distribution and use a non-parametric way to model the depth distribution, which can naturally handle both unimodal and multimodal distributions. Given the same distribution at the initial level, we select the depth hypothesis with highest probability and directly propagate them into the refinement level. This depth hypothesis will be subdivided and re-estimated on each refinement level, and the hypothesis with lower probabilities will be skipped. At the final level, we estimated the final depth as the expectation of this non-parametric depth distribution. Since the depth samples around the ground truth depth are preserved along the refinement process, our final depth estimation can be very close to the ground truth depth. For estimating the probability for each of the depth samples shown here, we design a sparse cost volume and sparse cost aggregation network. For a group of depth hypotheses that are selected from previous level, existing methods build flattened cost volume by directly concatenate the matching cost of selected hypothesis. Doing so can produce spatial ambiguity in the cost volume, since adjacent voxels of matching cost might not come from adjacent points in 3D space. For cost aggregation, the 3D convolutions will be applied on depth samples that have unrelated depths, which will further cause noise in the cost aggregation. Instead, we firstly build a sparse cost volume that retains rigid spatial relation. The sparse cost volume consists of the matching cost for the selected depth hypothesis, while keeping the unselected parts empty. We build a sparse cost aggregation network to aggregate cost utilizing the rigid spatial relation. The output is the sparse probability distribution for each pixel, which is used to build the cost volume in the next refinement level. This is the general pipeline of our network. We iteratively refine the non-parametric depth distribution for 3 iterations until we reach the input resolution, where we generate the final depth map. We train the network in a supervised manner. We use the depth probability distribution approximated by the high-resolution depth observations as ground truth. We use binary cross-entropy loss for the estimated probability distribution and L1 loss for the final depth estimation. The network is trained on the DTU and the blended MVS dataset and evaluated on DTU and the Tanks and Temples public benchmark. On DTU dataset, we achieved the best overall reconstruction quality and the best accuracy on boundary regions. Our method can produce sharp edge on boundary regions and accurate estimation of tiny objects. On Tanks and Temples dataset, our method also achieved competitive results and produced much better estimation for boundary regions and small objects. Our code will be released soon. Thank you.